So I'm going to talk about inference in mathematics. I'm a philosopher, so this will be from a philosopher's point of view. Am I pressing the wrong thing? So I'm going to talk about mathematics and the general theory of inference, deductive inference in mathematics, and then non-deductive inference. So the talk is about inference in pure mathematics, and mathematical inference is unusual in several respects, and it's quite different from the talk is quite different from the ones you heard this morning and earlier today, because mathematics is mathematical objects, for a start, they seem to be abstract. So numbers, functions, sets, geometric shapes, and so on, that pure mathematics is interested in, are not spatiotemporal, they're not causal, they don't seem to be causal. Therefore, mathematics is not a causal domain, so any kind of inference in pure mathematics is not going to be causal inference. There are correlations in mathematics, but the standard picture is that all the correlations are necessary. You know, if certain spaces have certain properties, well, that's just a necessary fact because it couldn't be otherwise. Deductive reasoning proof plays an outsized role in mathematics. So a general theory of inference has to cover mathematics as well as other kinds of reasoning, you know, scientific reasoning, everyday reasoning, legal reasoning, and so on. So suppose, let me give you an example from epistemology. Alvin Goldman in the late 1960s came up with this sort of short-lived account of knowledge, a theory of knowledge, which stated that you know something, if it's true, you believe it, and you're causally related to the fact in the right way. Now, this theory was not meant to apply to mathematics. It didn't apply to mathematics because mathematics, as I just said, is not a causal domain. A theory of inference, if it's going to be, suppose you want to come up with a general theory of inference, should you have that ambition, it's going to have to cover mathematics, which, as I said, is unusual in these respects. So just as a causal theory of knowledge could never have been a fully general account of knowledge, a theory of inference, which is just limited to the causal inference or to the physical case, is not going to be a complete theory of inference. Oh, I went the wrong way there. Okay. Or did I go the right way? I went the right way. Okay. So, like any other field, mathematics exhibits two very broad types of inference, right? So, this is just an obvious point. You can divide it into deductive inference, where the conclusion logically follows from the premises, or non-deductive inference, where it doesn't. And this is just non-deductive inference is just a catch-all category that anything that's not deductive. And I'm going to take a closer look at each with a sort of nod to my research as prompted by the organizers. So, what is deductive inference? Well, premises necessitate the conclusion. Necessarily, if the premises are true, the conclusion also has to be true. The starting points, if the starting points are true, then the conclusion will have to be true. And our best theory of logical implication or logical consequence adds something to this necessitation idea. It takes the necessitation to be true, to hold in virtue of form. So here's a very simple example of what I mean by that. Anne is either American or Brazilian, A or B, that's the form. Anna, is not American, not A, therefore Anna is Brazilian. Okay, so there the premises, if the premises are true, the conclusion has to be true, but not just that, it's in virtue of form. Any argument that has that form is also going to be have that property that the premises will, the truth of the premises necessitates that of the conclusion. So a very natural thought is that deductive inference is logical implication. Now, I've stated that very roughly, and that sort of breaks down into two halves. The first half is that when we infer deductively, we move from some premise or some premises to a conclusion that these premises logically imply. Okay, and that seems correct. But the second, so I put a tick next to it. But the second half, the other direction is not so clear. In fact, I think it does not hold. The second direction is that if some premises logically imply a conclusion, we can deductively infer the conclusion from the premises. Now, there's one sense in which that's true because, if you can assume that you assume we have all the powers that we need to follow a logical implication, then it holds. But if you're not talking about idealized versions of us, but human beings, even just mildly idealized versions, then that second equation is not going to hold. And more importantly, we need to sort of distinguish between implication on the one hand, which is a relation between statements, and that's not an anthropocentric notion. That's just what holds a property that some statements have and collections of statements have and others don't. Some premises entail a conclusion, or they do not. And there's inference, which is something that an agent performs, and which is anthropocentric by definition, even if we consider idealized agents. So here's a kind of general question. So what is logic? Well, implication is the realm of logic proper. Right? Implication, the relationship that some statements have to others, whereby they logically imply them, like in the Anna example, that's what logic is interested in. Logic is interested in implication. And what is that best theory of implication? By which I just mean, I use that interchangeably with logical consequence. Well, in a book that Owen Griffiths and I wrote, it came out last year, we argued that there's a correct logic and that it's highly infinitary. Okay, so what does that mean? Well, I'm not going to go into too much detail, but one of the things it means is that you can conjoin infinitely many statements or disjoin them. Standard logic, you can only conjoin or disjoin finitely many statements. And you can also, in infinitary logic, you can also quantify over infinitely many variables, if you like. Unlike a natural language, such as English, where sentences are a finite length. And this actually builds on work by Alfred Tarski and Guy Lachère, who's up next. So the point here is that once you understand the difference between implication and inference, that sets you free. It enables you to give an account of logical implication that isn't constrained by agents. Of course, the only reason we got interested in logic was because we were able to perform inferences. But once you realize that logic is not about what we can do, but is about what follows from what, then you can, for example, consider whether logic is infinitary, which I believe it is. Now, the logic of mathematical inference you can call that your home logic, if you like. Your home logic in a particular context, which you use for deductive inference in that context, is going to have to be a sub-logic of the correct logic, whatever that is, if you're going to reason correctly. Okay? And a home logic is an epistemic tool. It's going to be sort of much more down to earth. It might, for example, be first-order logic, otherwise known as predicate logic. So for those who don't know, first-order logic has names, A, B, C, so on. It has variables, X, Y, Z, predicates, F, G, H, Boolean connectives, such as negation, disjunction, conjunction, and it has quantifiers for all that exists. And all its sentences are of finite length. And this is a very standard logic, of course. And your home logic is going to depend on what you're using it for, right? So you might even use just propositional logic, which is just Boolean connectives. So much mathematical reasoning can, in fact, be modeled by first-order logic. Not all of it, but a lot of it can be modeled. And logicians have over the past century, come up with some pretty good models of mathematical inference using first-order logic. That's to say, as reasoning from first-order statable axioms via first-order logic appropriate rules to first-order statable theorems. Okay. So you've got to distinguish the logic that you use as an epistemic tool for inference from the sort of correct logic, which might be, the home logic might be just the tip of the iceberg in a particular context. Okay, now I want to move on to something else. Let's setting aside the logic. Talked about the logic in mathematical inference in my overview of mathematical inference that I'm giving you, inference in mathematics. How should we characterize the epistemology of deductive mathematical inference? What what are axioms and where do they come from and how do we know them? A traditional picture here is the Euclidean paradigm. Okay, it's inspired by Euclid's Elements from about 300 BC, and it sort of held sway for more, a couple of millennia. The Elements being a synthesis of ancient Greek geometry and mathematics more generally. And very roughly, the idea is, in mathematics, what do? You start from self-evident axioms via evidence-preserving rules, and you thereby infer some theorems. And you transfer the kind of evidence, this kind of maximal degree of evidence that the axioms have, down to the theorems. And as I said, this was a very prevalent picture of mathematical reasoning from Aristotle, at least from Aristotle, who actually is comes a bit before Euclid, to the 17th century and beyond. And there's a kind of, in the 17th century, there's a kind of Euclid mania. A lot of people write books with a title, the Euclid of this or the Elements of that, where they want to. Any form of knowledge has to be recast in this kind of Euclidean form for it to be respectable. And today, Euclideanism as a kind of paradigm of mathematical deductive inference is on the wane, but it had some proponents even in the 20th century, and there's some people that you might call neo-Euclideans. And so Wes Wrigley and I have reconstructed and tried to assess this Euclidean picture in this book that's going to come out next month. So what is this Euclidean paradigm? It can be expressed, we think, in these 7 principles, slightly simplified here, that all axioms and theorems are true. All axioms are maximally evident. Maximal evidence is preserved when you reason from premises to conclusion. There's a finiteness condition. The axioms have got to be finitely many. The axioms have to be general propositions. There's an independence condition that the axioms have to be independent. Each axiom has to be independent of the others. That's to say, if you had an axiom that you could deduce from the others, then it would be a theorem, not an axiom. Then it loses its axiomatic status. There's no need to state it as an independent axiom. And a completeness condition, which is a kind of slightly schematic. All truths of a certain kind can be inferred from the axioms. If you're axiomatizing geometry and you've omitted and you're not able to prove a particular fact that you already believe about triangles, say, then you need to supplement your axiom set. You're missing something. Euclideanism, this Euclidean picture no longer holds in full generality about mathematics today. Well, truth still holds. We still think our axioms should be true of their intended subject matter. But truth here mostly takes the form of stipulative truth. Okay. Think of the axioms of group theory. The axioms of group theory define what it is to be a group. So they are true of groups, but by kind of definition, by stipulation. If you think that one of the axioms of group theory isn't true, you've just sort of misunderstood what it is to be a group. The self-evidence principle doesn't apply generally because in foundational theories of mathematics, such as set theory, there are certainly some axioms that are not self-evident. The flow principle fails for sort of general reasons. Finiteness and generality usually apply, and independence, but independence does not apply generally. In standard axiomatic systems, there may be some dependency among the axioms. For example, in the standard system of set theory, there is some dependence between the axioms because other criteria such as simplicity and ease of comparison are desiderata that kind of override this independence desideratum. And completeness fails, we now know, for various reasons. It sort of depends on the version of completeness that you go for, but if you go for the sort of highest form of completeness, where you can deduce either a proposition or its negation in a kind of a system, other than the sort of very simple axiomatic systems, Gödel's incompleteness theorem is going to tell you that completeness is not going to hold. So what should replace Euclideanism? Well, the kind of move away from Euclideanism introduces a couple of ideas. First, the idea is instead of talking about self-evidence, think about intrinsic plausibility or justification on a conception. If you think of the structure of the natural numbers, you have a certain conception of the natural numbers, then principles can seem plausible on that conception or not, likewise with sets. And this actually, and notice that this allows, once you move from self-evidence to intrinsic plausibility or justification on a conception, intrinsic plausibility on a conception, I should say, you are thereby allow for degrees of plausibility as well. And also extrinsic justification should also be part of the mix. So here's where pure mathematics starts to look more like science. Extrinsic justification can be sort of divided into two broad categories. One is regressive. So this is analogous to the kind of justification that's enjoyed by a scientific postulate, which predicts the data. You've got some sort of mathematical data in the mathematical case. That could be very simple claims, simple arithmetic like 2 + 3 = 5, or it could be more sophisticated claims. And the idea is that an axiom gets to earn its keep by predicting some of these claims, just as in the kind of scientific case. But there's a theoretical form of extrinsic justification also exists and takes the following form, that principles can enhance the simplicity and economy and unifying power of the overall theory, and thereby are kind of justified in that way too. Okay, so talked about mathematics and general theory of inference and about deductive inference in mathematics, focusing on the logic and also on the axioms and what justifies the axioms and the kind of the old picture versus the new one that has emerged. I want to end by talking about non-deductive inference in mathematics. Okay, so remember that non-deductive inference is a catch-all category that encompasses any sort of inference that's not deductive. So there's some broad categories here. For example, enumerative induction, sometimes people just say induction, when you infer from all observed A's having been B's, in a very simple case, that all A's being B's, from the observed cases of A's having some property to the unobserved ones also having that property. Or there's inference of the best explanation, and very schematically, there's a body of established facts to be explained. And these facts can be a mixture of observations and more theoretical claims, and among a range of explanations, you should accept the best one. That's what inference of the best explanation looks like, and it's not deductive. Okay. There's a caveat here about the explanation having to be a good one. So what about mathematics? I mean, how does mathematics rely on non-deductive reasoning? Well, there's some obvious ways in which it does so. I mean, for a start, the choice of research project, for example. You should choose a research project that's tractable, either for you, a research project for you or your student. And by definition, the research project that you haven't proved what you might want to prove. Therefore, in the absence of a proof, you've got to kind of make a judgment about whether it's a tractable project or not. There's also what philosophers call testimonial knowledge or justification. So just like any other sphere of knowledge outside mathematics, Fermat's last theorem, for example, approved by Wiles and Taylor in the mid-1990s, is a 100-page paper. Only experts in the field can read it and understand it. But you and I know that it's true because the experts are a kind of reliable community, and therefore that knowledge can be passed on to us. And in fact, most mathematical knowledge is of this kind, whether it's sophisticated claims, proofs of such as the proof of Fermat's last theorem, or just simple ones for the sort of lay mathematician who knows Pythagoras' theorem because their teacher told them it was true, or the textbook told them it was true. There's also computer-generated, computer-assisted, computer-verified proofs. Really, this is just an example of the former, because you're assuming that the computer is the hardware, the software is reliable when you're relying on it to generate some result or to some calculation. And so 21st century mathematics will be severely hamstrung by a strict insistence on deductive reasoning only. I mean, this would be a kind of sort of proof fanaticism. Is there non-deductive knowledge in mathematics? Okay. By which I mean knowledge of a mathematical proposition without anyone having a proof of it, not just, not even Wiles and Taylor, but no one whatsoever, no computer having come up with it. So I think I take the sort of radical view that you can know a proposition without anyone having proved it. So mathematicians don't like this at all. In fact, mathematicians use the word know in a mathematical context synonymously with it's been proved, or we have proved. So, we've known since 2002 then such and such because someone proved it in 2002. But is that right? So take an example of, from number theory, Goldbach's conjecture, or the example of primality testing, where you test whether a number is prime, and then you can quickly convince yourself with probability 1 minus epsilon, where epsilon is really tiny, that it is prime. So Goldbach's conjecture states that every even number is a sum of two primes, every even number bigger than 2. So there's a lot of enumerative evidence behind it. 4 times 10 to the 18 cases have been tested. There's also evidence that the number of ways of writing an even number as a sum of two primes grows with that number, not in a kind of linear or strict way, but as an overall increasing trend. There's proofs of very slightly weaker theorems. There's heuristic arguments about the distribution of the primes that don't prove but suggest that the argument is true, that the Goldbach's conjecture is true. And there are also analogues of Goldbach's conjecture that hold in random models of the primes. So the probability that a number n is prime is 1 over log n. If you generate sequences of numbers with that probability, that's to say that number n appears on the list with probability 1 over n, you get a kind of prime-like sequence, and then you can have an analog of Goldbach's conjecture for that. And a version of Goldbach's conjecture holds with probability 1 for these sequences. It doesn't prove Goldbach's conjecture, but it does tell you that what the class of those sequences looks like. Also, you could come up with sort of philosophical arguments to diffuse objections to this kind of idea that you can know mathematical claims without proof. And one such argument is based on philosophical analyses of knowledge. So I mentioned one before, the causal theory. And as I said, that one doesn't apply to mathematics. Or to put it positively, it doesn't rule out non-deductive knowledge of mathematics either. And if you look at the kind of these philosophical analyses of knowledge, the things that have got some sort of traction in the literature over the last sort of 50 years, 60 years that philosophers have been thinking about this in a lot of detail. Of course, they did think about it before. But they sort of fall into two camps. Either they don't apply to mathematics, like the causal theory, or if they do, they allow non-deductive knowledge of mathematics. For example, the classic case of knowledge being justified true belief. You can have non-deductive justification, as in the case of Goldbach's conjecture. And actually, if you think about it, there's sort of non-deductive reasoning that's at the heart of deduction. Because as I said earlier, axioms are at least in part extrinsically justified. And this is a form of non-deductive justification. Right? If you believe something in part because it has some nice implications that you already believe, then you're not deducing it from some axioms. That form of justification is non-deductive. And so abandoning this Euclidean picture helps undermine the sort of specialness of deductive reasoning. If there's some sort of non-deductive justification behind some of the axioms, then the kind of what's special about deductive reasoning has been undermined. Another way in which there's sort of non-deductive reasoning at the heart of deduction is that mathematicians rarely give full proofs. Right? Especially expert mathematicians, they tend to give proof sketches. And so your confidence that a proof sketch can be elaborated into full-dress proof, where does that come from? If you give a proof sketch, where does your confidence come from? What does it depend on that it can actually be turned into a full proof? Well, just kind of your knowledge that this has worked in the past, or that steps of the kind of this size actually, if you spelt them out, would actually would actually be valid, and so on. So that's justified non-deductively. That's just from your experience as a mathematician. So let me summarize the 4 things that I've told you in my overview of inference in mathematics. Any general theory of inference, should you want to try and come up with one, has to cover mathematics as well, which is unusual in several ways. The second thing is that deductive inference isn't the same as logical implication. I take deductive inference to be something an agent does, logical implication to be a relation between statements. And I think, and you don't have to buy this, but I think that the latter is this highly infinitary. The third point was that Euclidean paradigm no longer applies wholesale to mathematics, a kind of a different picture of deductive mathematical justification is now much more current. And my fourth broad point was that non-deductive reasoning is prevalent in mathematics and is in perfectly good standing. Thank you.
Thanks. This is a really interesting talk. I was curious, just because you've characterized it as a Euclidean program, do you think that there's a central component of diagrammatic reasoning that's a part of, I mean, at least as Euclid originally did it, is that something that's important? Because there's some people who I think want to characterize that as possibly not being something you can regiment in first order logic. So.
Yeah, thank you. That's a really good question. Yeah. So the Euclidean paradigm, or the Euclidean foundationalism, as I described it, didn't say anything about diagrams. But Euclid, of course, in the Elements very much relies on spatial reasoning and on diagrams, diagrammatic reasoning. You can't really be convinced of many of the propositions unless you draw a diagram for yourself or see it on the page. And Euclid was criticized for that in the 19th century, and in the late 19th century especially, as kind of modern logic started to be developed. People realized that there were all sorts of gaps in his reasoning. So a kind of a new ideal for mathematical reasoning was born, whereby the steps in mathematical reasoning are actually logical, are deductively valid, and do not rely on diagrammatic reasoning in any kind. But I think the Euclidean, the way I wanted to characterize Euclidean foundationalism was broader than that. I think that's a very narrow way and a very kind of relatively modern way of characterizing mathematical reasoning. If you want to take in the history, much broader sweep of mathematics and understand why the Euclidean picture was so important and was so prevalent for so many centuries, I think you have to allow steps in mathematical reasoning that could be guided by spatial intuition, that are not strictly logical. When I describe mathematical inference, the deductive inference, that's a kind of much more modern way of thinking about it. Yeah.
I would like, should we move to tea and we can continue asking questions, so we're doing our best to stay in time, or we're going to regret it later in the day. So thank you, thanks for
All right.
the talk.